All right, let's get started. Okay, so first off, let me get the sign-in sheet passed around. Um, okay, so let's take care of some housekeeping. So first off, in regards to homework 4, I don't have that due for a while because of we're probably going to have some gaps in the lectures and whatnot, and just wanted to make sure that you'll have time to do that. Just so you're aware for what's coming. So homework number 4 is going to cover geometric properties and shear and moment diagrams. So we've covered all the geometric property stuff necessary for the homework assignment. I'm going to show you something on Excel here in a little bit, just so everybody has that available to you. Today we're going to talk about shear and moment diagrams, and I'll go ahead and tell you that if you're in structural analysis, which I know a couple people in here are, I'm just going to apologize because this is probably going to be somewhat boring today because we really did some shear and moment diagrams in there. And if you can do what we did in structural analysis, you can certainly do what we do in here. If you aren't in structural analysis, don't worry. This isn't going to be that bad. We take a pretty simplistic, basic approach in here. So let's talk a little bit also about just housekeeping when it comes to the schedule, just so everybody's aware. Okay, so that's the lecture schedule. I guarantee you at least one of these days is going to get canceled. Definitely, I'm just going to tell you, it's going to be one day next week. I don't know when. So just be patient with me. Pay attention to your class emails. I'm going to say to you what I've said to all my classes. If you don't hear from me, we're having class. So unless you hear from me, make sure and show up. Sound good? Okay. Now, I do want you all to get a little bit of an eye on the prize down the line. So homework number 4 is going to be geometric properties and shear and moment diagrams, and then homework number 5 is going to be bending and shear stresses. And that is the exam. That's exam 2, because those topics sort of go very well together. And then, honestly, exam 3 ends up being just sort of a hodgepodge of everything that's left, like stress analysis and Moore circle and column buckling and things like that. But I do want you to see sort of an overall goal as to what we're talking about. So I don't think I need to go into day 1 why we're in this class. I mean, I think we all know by now, the value of the material that we're learning in here. But what we've been talking about over the past couple days has a much different flavor than what we were talking about near the beginning of the semester. Because near the beginning of the semester, we were talking about stress and strain and whatnot. And we haven't brought that up in a while. So I do want you to see sort of an eye on the prize. Here soon, we're going to derive our final 2 fundamental stress formulas. So we've already derived 2 of them. We derived one for axial loads, the stress being P over A, and then we derived one for torsion, the shear stress being TR over J. And those are pretty straightforward. I could derive the bending stress and shear stress formulas for you right now. The problem is that in order to implement them and properly use them, you got to understand some pretty fundamental background information, okay? For instance, let's take the bending stress formula. Okay, so the fundamental bending stress formula that we're going to use is sigma equals my over I. Sigma equals my over I is without a doubt one of the most popular or most fundamental stress formula, it's one of the most commonly known stress formulas in existence. It's like if there's any one formula that you as an engineering student should remember, like throughout your career, it's like everybody remembers sigma equals my over I. It's that fundamental. It's like sum of moments equals 0. It's like it's that fundamental. But in order to properly use it, you need 2 really fundamental quantities. You need to know the moment of inertia, and that's not as simple as just a number. There's some work that goes into determining a moment of inertia, and I think that you've been convinced of that over the past couple of days, because we've been taking composite shapes and determining those centroidal moments of inertia, and that's not something that happens, just, oh, there's the value. I mean, that takes a little bit of work. But you also need to know the distribution of loads on the structure, namely the moments and then also the shears, okay? And so these stress formulas, they take a little while to properly derive. So you have to sort of take a step off to the side and talk a little bit about, let's say, the geometric properties. And now we have to take another step to the side today and talk about shear and moment. So once we've discussed geometric properties and shear and moment diagrams, then we can sort of get back into the swing of things with stresses. So I want you to see sort of a start to finish approach, like why we're covering what we're covering and whatnot. So let's talk about shear and moment diagrams, okay? Now, I've got the feeling that you all have been exposed to shear and moment diagrams before. Like, it was probably very quick, and you didn't spend a lot of time on it, and usually the problems you dealt with were pretty simple, okay? So what I'm going to do in here is I'm going to go through a graphical approach to determine how to plot a shear and moment diagram. Again, for you folks in structural analysis, you've actually already seen this, so I understand if you're like, oh goodness, not again. But for you folks in mechanical who have probably only seen this from a statics perspective, you may not have been exposed to this graphical approach. So I'm going to sort of derive for you how it works, and then we're going to have some pretty basic examples explaining its application. So, you know, these metrics for engineers, you know, graduating with a degree, and you know, it's like, for instance, if you graduate with an engineering degree, a civil engineering degree or a mechanical engineering degree, you will know what Bernoulli's equation is, okay? Now, for those of you who aren't in fluid mechanics, you don't know what I'm talking about, but you will know about Bernoulli's equation down the line. It's like one of those fundamental skills that all engineers understand. And there's other fundamental skills, like for you mechanicals, you'll know, what are the laws of thermodynamics and whatnot. They're pretty basic stuff. Well, another very fundamental basic skill for an engineer is having the ability to draw a shear and moment diagram. It's like anybody who graduates with an engineering degree, anytime, anywhere, it's like everybody knows this is like a fundamental skill. And the reason why is because in order to properly design anything that's being bent, a beam, a frame, any element in any system that is experiencing bending or transverse shear, you need an understanding of the distribution of shears and moments across that element in order to design it. So, those fundamental stress formulas, sigma equals my over I. We get the I from all the section property stuff that we talked about earlier. How do you get the M? Well, it comes from shear and moment diagrams. It's the value from the moment diagram. Okay. Now, I'm going to derive for you the graphical approach to how to do this. So I've got a beam, some random structure, and it's being subjected to some load. It doesn't really matter what it is. So we'll say the load is represented by some function, some W of X function. Sorry, I'm going to look at my phone, I promise you. I got a lot going on. All right, so I've got a structure that's being subjected to some load, and I've got the load going upward, and I'm only doing that so that if you look at the coordinate system, you'll see that the positive y-axis is going up, so the load is positive, okay? Now, I'm going to take a little bit of a differential approach, so you all should remember from calculus how you can cut out a little differential slice of that structure, like a little element that's like dx wide. So, over here, or down here on the bottom, I've got dx expanded, and I've got it, plotted like it's, this wide. But remember, dx is a little itty-bitty tiny width, like it's super tiny, okay? It's differential, it's infinitesimal, okay? And that's important because I'm going to cancel a term here in a second, and I want you to keep in mind that this term dx represents a distance that's itty-bitty-bitty, okay? Now, a couple other things to keep in mind. Because that differential element is itty-bitty-bitty-bitty-bitty, it's really, really tiny, the load, I know, is variable. It changes across the span. But over that really, really tiny, tiny interval, we can assume that load is constant. So I have a constant load of W being applied across that differential element. Now, what I'm interested in really when I do this is I'm not really interested so much in the shear or the moment, but I'm interested in how much the shear and moment changes from one side of the element to the other. See, I propose that if I look at the shears, well, I've got some shear over here on this side of the element, but on this side of the element, it changes. So if I've got V over here, I'm saying V plus some incremental change in shear. And so that's really what I'm trying to determine is what are those changes in shears and changes in moments. And so when I look at those that element, basically what I'm proposing is that those values are going to change from one side of the element to the other. And in order to determine them, I'm just going to use the basic equations of equilibrium that we've been using from square one. So let's just walk through this. I'm going to take my time with it. So I got two equations, sum of forces in the y direction and sum of moments. So let's deal with the sum of forces in the y direction first. Okay, so we'll take our time with it. So here's our element. Okay, and remember, you know, sum of forces in the y direction equals 0. Basically what we're saying is everything going up's got to equal everything going down. So what do we have going up? Well, we've got V going up, and we have this load going up. Now, it's not W. Remember, that's a distributed load, okay? A distributed load is like kips per foot. So I have to multiply that by the length to get the total amount of force. So W times dx will tell me the total number of force. So I've got V going up, and I've got W dx going up, okay? And what do I have going down? Well, what I have going down is this V plus dV going down. So everything going up has got to equal everything going down. The V's cancel, and that incremental change in shear is W dx. Everybody okay with that? Okay, now what about sum of moments? Now, in order to make my life a little easier, I'm going to sum moments along the right side of this element. So we're summing moments. Everything spinning clockwise got to equal everything spinning counterclockwise. So what do I have? Well, I've got moment spinning clockwise. I've got V times dx spinning counterclockwise, and I've got this load spinning counterclockwise. So the force is W dx, and what's the moment arm? How far is it from this side to the center of that load? Well, it's half a dx, right? Okay. Now, as for things spinning this way, well, I've got m plus dm spinning this way. I don't have to deal with this force over here on the right because it's going right through it. The distance is 0. So chug it out, and I get the equation that you see here. Now, if you notice, I've got a line through this W dx squared over 2, okay? There's a reason for that, okay? Remember, dx is a distance that's super, 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 super tiny. Remember, really tiny, okay? Let's go back to basic math. What happens if you take a really small number and you square it? What do you get? A really, 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 really small number, right? Like it's super tiny. So I propose that if you're dealing with an infinitesimal element that's super, super tiny and you square it, that term is so negligible that I can just cancel it, okay? So I propose then I get the following relationship. I get that dV is W dx and dm is V dx, okay? Now, you can probably look at these and see where this is going. I can take these definitions and sort of rewrite them as derivatives and integrals. Now, what I'm going to do is this. Instead of using some sort of hyper fancy calculus approach with this, I'm going to take a pretty straightforward, basic graphical approach into looking at this. Okay? So let's just sort of take this one step at a time. So I propose that the derivative of moment is shear. And I propose that the derivative of shear is your load. Vice versa, if I integrate the load, I get the shear, and if I integrate the shear, I get the moment. Okay? So from that, I think I can make a few observations. Okay? Let's look at the relationship between load and shear. Okay? Because the way this is going to work is we're going to start off, so I'm going to skip ahead a couple slides just so you're aware. So we're going to start off with a structure like this. Okay? And so that's going to be our loads. From these loads, we are going to obtain a shear diagram, and from that shear diagram, we're going to obtain a moment diagram. So it's going to go step by step. So let's see if we can define the relationship between load and shear. Okay? Well, at any given point, whatever the value of the loads are, that equals the slope of the shear diagram. Okay? So this is going to require a little bit of an understanding from you all about slopes. Like, remember, positive slopes go like that, negative slopes go like this. Like, what's a zero slope? That's when it goes flat. So you're going to kind of need to know that, okay? And then between any 2 points, the change in shear is equal to the magnitude of load. So if you understand that, when we go through shear diagrams, like when we go from a load to a shear diagram, like if you keep these philosophies in the back of your head, you'll see how we're actually using these pretty directly, even though it might not seem like it. Okay? Now that's between load and shear. What about the relationship between shear and moment? And I can leave this up here if anybody needs a minute. So, everybody good? All right. So between shear and moment, what's going to happen is this. We're going to have a shear diagram, and then we're going to need to plot the moment diagram. Well, it's going to be pretty straightforward. The value on the shear diagram is going to equal the slope on the moment diagram. Again, it goes from derivatives. Then as for changes in moment, well, if you want to determine the change in moment between point A and point B, just integrate the shear diagram between point A and point B. Now here's the thing. We're breaking out a lot of calculus terms and breaking out, these terms like differentiate and integrate, and you're like, Dr. Mike, we've already had Calc 1, Calc 2. Come on. It's 8 o'clock in the morning. Haven't had my coffee. Do we really have to do all this integration? The answer is most often, no, you don't. Because keep in mind, when I say integrate, the term integrate means determining the area under the curve. Well, a lot of these curves are not really going to be curves. They're going to be basic shapes like rectangles and triangles and things like that. So we can determine the area without having to break out, the integral evaluated from A to B. It's going to be a lot more straightforward than you think. Now, this next set of slides is probably a little rote. I think just about everybody in here knows what's going to be on these next slides, but I sort of want to formalize it just to make sure that we're all on the same page. So in order to determine the distribution of shears and moments on a structure, you're going to need to determine support reactions, and that means having an understanding of support conditions. So for instance, we're going to have at most 3 types of support conditions that we deal with as civil or mechanical engineers. And one of the things I want to keep in mind right off the bat, and I say this in day 1 instructional analysis, but I haven't really said this in here. I want you to keep in mind something that's very, very important when we assess something as engineers. The stuff that we're analyzing, when we have a gear shaft and we're trying to determine the amount of torsion on that shaft, or we're trying to determine the shear and moments on beams, what have you. I want you to keep in mind that we're not really analyzing the systems themselves. What we're doing is we're analyzing these mathematical models that we've created that represent these systems, okay? And I know that might seem like you're splitting hairs, Dr. Mike. Come on, this is ridiculous. Not really, okay? What's going to happen very often for you as an engineer is you're going to be given just some system. Like if you're a mechanical engineer, here's a camshaft, figure it out, And there may not be some straightforward basic, oh, that's a simply supported beam, or oh, here's the boundary conditions. It may not be that simple. So you as the engineer or as the analyst or as the designer are going to have to figure out, okay, what analysis model represents this structure as closely as possible. So it's something I want you to think about. These pin supports and roller supports, like I've got some physical examples in these images here, but even these physical examples have some real-life caveats to them. For instance, a pin support. We idealize a pin support in engineering as one that restricts motion in the X direction and the Y direction, but it allows rotation, okay? So I think this image here on the right would be something that I think most engineers could conceptualize as one that's very easy. That obviously it can, it restricts motion in the X and Y direction, but that it can rotate across that pin. But for you civil engineers, we idealize this one on the left as a pin condition as well. And you think, well, now hold on, you've got 2 bolts on the end of that beam. That's going to resist that bending a little bit. The answer is, yeah, but not very much. And this is one of those statements I'm going to say where you're going to have to trust me, because later on we're going to derive these formulas. But long story short, whenever you're looking at an I-beam, the primary amount of bending or moment or rotation is carried by the flanges. And if you notice here on this connection, the top and the bottom aren't connected. So we can assume that that connection from an analysis standpoint doesn't really transfer moment. Now, it transfers shear like nobody's business, okay? And so that's sort of the difference there. I just want you to sort of think, you know, a little bit realistically about this. Now, this would be an example of a pin support. Here's a roller support. A roller support only restricts motion in the direction of the roller, but it allows rotation and it allows lateral movement. I hate to keep referencing things to bridges for you mechanical engineers, but one common example of pinned and roller supports in the real world is when we have highway bridges. Usually, if it's just like a simply supported bridge, like you just have a support here and a support here, we'll have what's called a fixed bearing on one end and an expansion bearing on the other. And the difference is, so you have the bridge and you have a plate that connects it to the abutment in the ground. Fixed bearings just have a hole in the plate, whereas expansion bearings, the hole isn't like this, it's sort of like a slotted hole. So the bridge can sort of move along the axis a bit. And the reason we do that is because of temperature. Over the design life of that bridge, the girder will get hot and get cold and it'll want to expand and contract. So we actually want to allow it to move a little bit. If not, you'll start to get some thermal stresses built up in that girder, and those stresses can get pretty heavy pretty quick. And usually what ends up happening is you end up either failing the girder or failing the abutment, and so that's no good. So there's a real life example, but I just wanted you to sort of get a flavor for that. As for our third support condition that we consider is a fixed support, okay? So a fixed support is one that resists everything, resists rotation and resists movement. So anytime you have a fixed support, there's going to be at most 3 unknown reactions: an unknown reaction in the X direction, an unknown reaction in the Y direction, and an unknown moment reaction. For you structural analysis folks, one of the things that you're going to see in here is you're never going to hear me talk about internal hinges. We're not going to see any weird triangular loads or whatnot, because in here I want that part of the problem to be a little simple, and what I want to focus on in here are the resulting stresses, because that's sort of our goal in this course. Any questions? Everybody got this? Yes. Usually, but keep in mind, if you're calculating, let's say you're going to get this much deflection, well, your slotted hole usually ends up being a lot bigger than that because it allows either way. So, but yeah, I'll tell you a funny story. A buddy of mine works at a Kokosin Construction, which is a bridge. They do a lot of heavy bridge construction. Anybody know of the Nitro St. Albans Bridge, the big one? Okay, those beams are like 11 feet deep. Think an I-beam that's taller than this room. That's big. Okay, so here's the reason I tell you that story. The way that they constructed that structure is they started from one end and the other and erected it in pieces. I mean, how long is that bridge? Anybody have an idea? A guess. I mean, we're talking hundreds of feet. Nobody, what's that? Yeah, it's a long structure. No way, shape, or form are you going to just erect that structure in one piece. You can't truck a 1,500-foot piece, you know, down Interstate 64, you know. So it comes in pieces, and so they started at the end and they got to the middle. Well, they got to the middle and they lifted in the last piece and they realized it was too long. Okay, so you can imagine that your construction foreman was sweating bullets that day when they had, you know, this multi-million-dollar project and they get to the middle and it's too long. So you want to know how they fixed the issue? Well, it was 95 degrees that day. So how do you get that girder element shorter when it's 95 degrees? You dunk it in the river. So they dunked it in the river and cooled it down and it contracted. They put it in. I thought that was like, I was like, now that's engineering. Yeah. And don't tell the environmental folks that because they might. Actually, yeah, I don't even think that was an issue because the girder had already formed its patina, so it wasn't like that was going to be a thing. So yeah, and it's not like they left the girder in the river for, you know, days. They put it in there for like 10 minutes or something, just to get it to cool its ambient temperature. But yeah, that's how they did it. So I thought that was a really cool and innovative and simple solution to a really challenging and problem that would probably make some engineers on site really nervous. So absolutely not. I'm saying that once constructed, the bearings allow it to move a little bit. But at the time, you know, you're trying to fit it up, and you've got a girder weighing, you know, 5, 10, 15 tons hanging in the air, and it doesn't fit. Like, how do you make it fit? So yeah. All right, that's all I got. Okay, let's get into it. I want to draw the shear and moment diagrams for these examples. Now, one of the things that you're going to find is this when we do these problems. For instance, point B is a pin support. So it has an unknown reaction in the x direction and an unknown reaction in the y direction. But can anybody just look at that structure and tell me what Bx is going to be? 0. There is no forces going in the x direction. So I'm actually going to kind of ignore that a little bit. And what I'm going to do is determine the reactions and plot this accordingly. And I think you're going to see this is pretty straightforward. So let me go ahead and draw this out. Don't worry, I will make sure and give you all time to dictate this out. Excuse me. Okay, so we have a distributed load that, let's see, 4, 6, 6, 3. And then something like that. Okay, and this is, I think it was 2,000. This is 4,000 pounds. And this is 400 pounds per foot. This is A, B, C, D. Now, here's one thing I'm going to go ahead and do. I'm going to say we need to determine BY and we need to determine CY. Okay? And here's our dimensions. Four feet, 6 feet, 6 feet, 3 feet. Okay. One of the things I did on this problem is this. So I have the following loads applied to this structure, okay? And I have these reactions I need to determine. Now, I have a reaction at B and a reaction at C. Now, keep in mind, I also have a horizontal reaction here at B, but since there's no horizontal loads, we'll just say that's 0, because I think that, and it's not going to affect our problem anyways. One of the things I did, and I just sort of just did it, is I just said, you know what, let's just draw BY and CY acting upwards, okay? Now, what I did there is I made a guess. I assumed that BY and CY was going to act upward. If I do my math and I get a negative answer, it does not mean I need to develop significant emotional distress. All it means is that if my answer comes out negative, I assumed incorrectly and it's actually acting downwards. So don't, if you, when in doubt, just assume everything acts upward and let the signs fall where they may. Okay? Everybody okay with that? All right. Okay. Now, before I sum moments to determine reactions, one of the things I can do is deal with that distributed load right now. Now, I have 400 pounds per foot. How far of a distance is it acting over? It's 4, 6, so 16 feet, okay? So what I can do is, in order to make my computation of moments a little easier, is I can collapse that into a single point load. So 400 pounds per foot over a distance of 16 feet is what? 6,400 pounds, okay? Now, what I'm going to do is I'm going to say that that occurs about right here. And so that's 6,400 pounds. And how far is that from A? 8 foot. Now, let's be clear. I can put this here when I'm determining reactions, but I want to be absolutely crystal clear. That 6,400 pounds does not exist, okay? It is not a real force on the structure. I put that there to make my computation of support reactions a lot easier, but it does not exist on the real structure, so that's just a point that needs to be made. Okay, now, in order to determine these support reactions, what I'm going to do is I'm going to sum moments at one location to determine the reactions at the other. So let's sum moments at B to determine the reaction at C. Again, breaking out my little table. All right, so this might be a little different, you know, for you mechanicals, since you haven't seen me do this before. You civils are getting tired of it already, I know. All right, so we're summing moments at B, and so we just take the structure, you know, take each load one at a time. So let's start off with that 6,400 pounds. So I'm at B, that's causing moment in this direction, and from B, how far is that 6,400 pounds from B? 4 feet. So I have 6,400 pounds times 4 feet, which, by the way, hashtag sign, you know, it used to be called pounds, so you can, yeah. Only 31, but still I know people are like, what are you talking about? All right. 2,000 pounds also causes moment in that direction. How far is that from B? 6 feet. And then the 4,000 pounds, keep in mind that 4,000 pounds at the very, very end, that causes moment. And how far is that from B? Well, it's 6. 6 is 12, 15, right? Not too bad, right? All right. And then that has to be resisted by CY that has a moment arm of 12 feet. Everybody okay with that? All right, so somebody help me out on this column on the left, because let's see, 2,000 times 6, that's 12,000. What? All right. This is 60,000. And this is 25,600. So adding those up, what do I get? I get 60, 72, 72, 97,600. Did I do that right? All right, so 97,600 foot-pounds, or that's foot times pounds. It's not pounds per foot. That's CY times 12 feet. And so what's that divided by 12? First off, it's positive, so. And so that's 81.33, or 8133.3. Pounds up. Everybody got that? All right, now, we sum forces in the y direction. All right. Let me move this over just a little bit. Okay. So everything we've got going down, I've got 6,400 pounds. I'll write the little pound sign this time, or elbs. 2,000 elbs and 4,000 elbs. I have BY going up. I have CY is 8133.3. Put pounds on there because I'm running out of room. So BY plus 8133.3 pounds equals 12,400. Did I do that right? So BY is positive what? $42.67. Do I have a second on that? Or 66.7. Do I have a second on that? All right. And so that's 66.7 pounds. Come on. I can do better than that. Up. Sound good? All right. Now, what I'll do is I'll go ahead and put this here. So this is 8133.3. And this is 4266.7. Okay. Now, in fairness, I did go through that kind of fast. So does anybody have any questions on this? Everybody okay with this? All right. Okay. Now, all right, I'm going to give you all a sec to write this down, and then when I do the shear diagram, I sort of want everybody to sort of watch what I'm doing because it's a lot easier to follow, okay? And I'll give you time to write it down. Don't worry. Okay? So watch what I'm going to do. Right off the bat, just so you're aware, when we draw shear diagrams and moment diagrams, this image is going to like go down, so I'm going to have a lot down here and a lot down here, so when you're putting this on your paper, just keep in mind that that's going to be the case. Okay. So here's what I'm going to do. Okay, so the first thing that I do is I draw these sort of little dashed lines. When I do it by hand, I draw like soft lines to sort of just guide what I'm doing, but yeah. And then I start off and I say, okay, here's my shear diagram. So I start off and I put this, and I'll say that's my 0 axis, okay? Now, we'll say that this is my shear diagram, and all the numbers are going to be pounds, okay? Now, all right. So don't worry, I'll give you time. So everybody watch me up here. Okay. All right. So whenever you draw a shear diagram or a moment diagram, okay, it's got to start at 0 and it's got to end at 0. Okay? Now, so watch how this works. We start at 0 over here on the left, and when you're drawing this out, you know, if you've got different colors or different colored pencils or whatnot, that's great. Most engineering students don't. So what I do is I like to put like little dash marks or arrows on this line because it helps me keep my eye focused on what's 0 and what's not. Okay, sound good? Okay. Now, when you're drawing a shear diagram, so this is what I want you to do. When you're drawing a shear diagram, you do what the beam tells you to do. Okay? So let's start off. I start at 0, and then the beam tells me to what? Tells me to go down, right? Okay. Now it tells me to go down at a rate of 400 pounds per foot, okay? So that's a straight line, okay? So what I'm going to do is this. I'm going to go down 400 pounds per foot, go down 400 pounds per foot to right there, okay? Now how far down have I gone? Well, if I'm going down 400 pounds per foot for 4 feet, that's what? 1,600? Okay. So what happens is this. The beam says go down, go down, go down, so negative 1,600. Okay? And then I'm looking at the beam, and the beam says, Greg, go up. And I say, okay, all right, chill out. All right? So if I'm at negative 1,600, and the beam says, Greg, go up 4266.7, so if I'm at negative 1,600, I go up 4266.7 right here. That puts me at what? What would that value be? If I'm at negative 1,600 and I go up 4266.7, what would I be at? 2666. There we go, 2666.7. So this is 2666.7. Okay. Now, the beam says Keep going, keep going. Remember, this is where you got to make sure you're paying attention. That's 6,400 pounds. That does not exist. We put that there to make our lives easier. So if you have to redraw it or erase it, go right ahead. In fact, I'm going to erase it because I don't want it to confuse me. That is the deal. Okay, all right. So now the beam says, okay, keep on going down, keep on going down, keep on going down, keep on going down. Okay, so where am I at? Okay, you say 266.7. Why do you say that? So there you go. So 6 feet at 400 pounds per foot, so that's 2,400 pounds. So if I'm at here and I go down 2,400 pounds, actually my scale's horrible. It actually should be a little more like this. Actually should probably be a little more like that. And so that is 266.7. And then what does the beam do? The beam says, Greg, go down. I say, okay, I'll go down. All right, so if I'm at 266.7 and I suddenly drop down 2,000 pounds, what's that put me at? Somebody tell me, somebody else. 1733.3. Does everybody follow along with me on this? Okay, so that puts me right about here. Excuse me, goodness. Okay, then I keep on trucking, right? Keep on going down. So where am I at here? Well, I'm at negative 1733.3, and I've gone down how far? 400 times 6 is 2,400. So if I'm at here and I go down another 2,400, what's that put me at? Somebody else. 4,133. There we go. Negative 4133.3. So this is minus 4133.3. And now what? The beam says, Greg, go up. No, it doesn't say go to 0. If I'm at negative 4133.3, what's the beam tell me to do? It says go up 8133.3, right? So if I'm at here and I go up like 8,000, it's going to put me plumb up here. What's it going to put me at? 4,000. Okay. Now, so that's one heck of a jump. I'm like all the way up here. That's 4,000. Now what? What does it look like from here to the end? Well, is there any load in between C and D? No. So if there's no load, I'm not doing anything. So I just go on over. 0 load, 0 slope. What does a line with 0 slope look like? It's flat, right? So I'm just going to go over to 4,000, go over right here, and then what's the beam tell me to do? Drop back down. And that'll put me at 0. What do you think? That's not bad, right? Now, one way that you can tell that you've done this right, well, there's 2 ways you can tell that you've done this right. I'll tell you the first one. The first way is that you will always start and end at 0. Always. Why is that? Because the sum of forces in the y direction equals 0. That's what that means, okay? The fact that you started at 0 and you ended at 0 means that the sum of forces in the y direction equals 0. Sound good? Now, so everybody follow along with me. In order to determine our next step, which is to determine the moment diagram, we have to integrate the shear diagram. But that's all simple shapes. So let's just determine areas. Now I'm going to do it in a little bit of a backwards order because I want to start with the easiest sections first. What is the area of this rectangle right here? It's 3 foot wide, 4,000 tall, so what is that? 12,000? Now watch what I'm going to do. I'm going to say that's 12,000 positive. Okay? Next one. Okay? Let's look at this triangle over here, way over to the right, this one right here. How do we determine the area of a triangle, right? Base times height over 2. So how tall is this little triangle? It's 1,600. And how wide is it? 4. So what is the area of that triangle? 3,200. And I'm going to call it negative because it's below that line. So we're going to say this is negative 3,200. Sound good? Okay. Now, for these shapes here, there's 2 ways of handling it. We could split it up into a rectangle and a triangle, but I'm feeling kind of lazy. Does anybody remember how to determine the area of a trapezoid? Anybody remember that? In other words, could we just take the average of that and multiply it by the length? Y'all remember that? In other words, kind of like if you cut that off and sort of flip it over. Well, we could split it up if you want. It doesn't matter. But I just want to know what's the area under here. I'm getting some puzzled looks. Did I go too fast? Everybody okay with that?
What do you mean by average for the area?
All right. So if you have a trapezoid that looks like that, okay? And this is the base, right? And this is height 1, and this is height 2, right? You can determine the area by taking the base times the average height. So how that works is this, okay? What you're basically doing is you're taking this triangle and you're sort of putting it here, right? And so what is that height? Well, it's the average of those 2. That's basically what you're doing. Is that fine? Everybody else okay with that? So what's the area under this first region, this one over to the left? The 88. Okay, so basically, like because we didn't track decimals, would you be in agreement that that's basically going to be 8,800? Did I get a second on that value? Anybody? Now, somebody else. I did it twice, 2 different ways. Okay, all right. What about this one down here? $17,600. Do I have a second on that? Okay, all right. Now, first off, you want me to give you all a minute to catch up? Y'all need a minute? Okay, all right. Okay, everybody okay with these areas? Now, so remember I said that there are 2 ways to check if you've drawn a shear diagram correctly. The first is that you always have to start at 0 and you have to end at 0. That's the first way. The second way is to look at the areas, okay? Add up all the positive numbers and tell me what you get, the positive numbers. You said 20,800? Now add up the negative numbers. 20,800. So if you were to add up all of the areas, what value would you get? 0. Why is that? Because the sum of moments is 0. Remember, in order to determine the moment diagram, we find the area of the shear diagram, okay? So the values on the shear diagram basically reflect that sum of forces equals 0, and the area under the shear diagram reflects that sum of moments is 0. Is everybody okay with that? That's a neat little check to see what you're doing is right. Now that's going to sound a little contradictory when we look at our next example, but our next example has a little caveat that's going to clarify that. So just keep that in mind. All right. Everybody got this? All right. Now what I'm going to do is this. I'm going to drag this down a bit. Okay. Now, I'm also going to take this and move it up ever so slightly so that I got just a little more room. All right. Okay. I'm going to let everybody get everything set up, and then I'm going to have everybody watch what I do. This is one of those sections where you got to watch. So take your time. Take your time. Okay. I still see a couple people getting this set up. All right. So everybody got this set up, or you need a minute? It's okay for you. Okay. All right. Okay. So everybody watch me. Before I draw any lines or curves or anything like that, I'm just going to indicate the values, okay? Because that's really easy. So again, my attention's going different places. All right. So start at 0. Okay. So watch this. Okay. I'm going to start at 0, and then from A to B, I know I'm going to go down 3,200, okay? Then from B to C, if I'm at negative 3,200 and I go up 8,800, what does that put me at? Plus 56. Now, if I'm at 5,600, draw that down a little bit. If I'm at 5,600 and I go down 17,600, what does that put me at? There we go. So that's minus 12,000. And so that positive 12,000 is going to bring me back to 0. That's okay, right? Okay. All right. Now here's where you got to put your thinking caps on. Okay, we got to think in terms of integrals. Okay? Now, just bear with me for a sec. What's the derivative of x squared? 2x. Okay, so if I wanted to graph x squared, what would it look like? Parabola. Okay, and what is the derivative of that graph look like? A line. Everybody okay with that? Okay, so here's a more general relationship. Would you agree that if I have a parabola and I take the derivative of that parabola, it's going to be a line? Okay with that? So on the flip side, if I have a line and I integrate it, I should get a parabola. Here's my point. I propose that this region, and this region are all going to be parabolas because they are lines, okay? Take the integral of a line, you get a parabola. What about this region? This region is a constant, okay? Let's take that 2x. What's the derivative of 2x? 2. So the graph of y equals 2x is a line, but the graph of y equals 2 is just a constant value, right? So would you agree that the derivative of a line is a constant? And vice versa, that the integral of a constant is a line. Like what's the integral of 2? It's 2x, right? So right off the bat, I would say that this last region is going to be a straight line. That's a straight line. That's easy. And I'm trying to draw that as straight as possible because of what we've got here. Okay. So far, so good? Now, so if these regions are a parabola from here to here, here to here, and here to here, we have to ask a question, okay? Let's take this first region, okay? If it's a parabola, I propose it's only going to go two ways, from here to here or here to here, right? It's only going to be one of the two, here to here, here to here. I am now going to introduce you to my highly scientific language or phraseology called little to a lot or lot to a little, okay? Here's what I mean. The magnitude, so looking from here to here, the magnitude of the shears, how big the shears are, go from a little to a lot. So I propose that the slope here, little to a lot. So I propose that in that region, the shear diagram looks like that. All right? What about the next region? What do the magnitudes look like? Lot to a little. Lot of slope, remember a line with a high slope, lot of slope to a little slope. So it looks like that. Next region, magnitudes. Little bit of shear to a lot of shear. Little bit of slope to a lot of slope. And there's your shear moment diagram. Boom. What do you think? Are there any questions on that? Okay. Let's make an observation from an engineer standpoint, and let's talk about design. Okay? Why the heck do we care about all this? Okay? As an engineer, okay, what you need to be able to determine are the maximum values of shear for design and the maximum values of moment for design. Okay? So if I'm the design engineer, okay, if I'm the design engineer, first off, we generally care more about magnitudes, okay? So whether it's like positive or negative, in general doesn't really matter, okay? So for shears, I propose that I'm going to design this for a maximum shear of 4133.3 pounds, because that is the largest shear value on the beam, okay? So 4133. So if you want, you could say that Vmax is 4133.3 pounds. And if you want to put the negative on there, that's fine, okay? But I don't want you to think, well, what about the 4,000? Really, we care more about magnitudes in this case, okay? Now, as for moments, I propose that our maximum design moment is minus 12,000 foot-pounds. Okay, so if you want sort of like an observational answer, that is one. Now, let me say a couple things about the sign, okay? First off, let's talk about shear. Do positive shears or negative shears, does the sign really matter from a design standpoint? Got a short answer for you. No, not really. Because here's the thing. All we're talking about in shear is whether or not you're shearing it this way or shearing it this way. It doesn't really matter. The beam is experiencing the same thing. If you want another way of looking at it, let's say here's my beam right here. Here's my beam and it's experiencing all these loads. Positive, negative shears really can change whether or not I look at the beam like this or I look at the beam like this. But in the end, the beam is still seeing the same thing. So positive versus negative shears doesn't really matter. Okay? Now, What about moment? Do positive versus negative moments really matter? Well, if you have a beam that is comprised of a single material and it's symmetric, like if I have, let's say, a solid circular bar and I'm bending it like this, does it matter whether it's positive or negative? No, it doesn't matter. There are instances where the bending moment direction does matter. Okay? A very common instance is reinforced concrete design. See, concrete is a material that behaves very, very well in compression, but when subjected to tension, it behaves very poorly. So in reinforced concrete design, we counteract that by placing rebar in the concrete. We place rebar in regions where the concrete experiences tension. Well, we have to know which direction the beam is being bent. If it's being bent this way, where the bottom is in tension, we put the rebar in the bottom. If it's being bent like this, we put the rebar in the top. But that matters based on the sign, okay? So I'll say this. Does the sign for shear matter from a design standpoint? No. Does the sign for moment matter? In some cases it does. In some cases it doesn't, but in some cases it does. In cases of symmetry and single materials that don't really behave differently from compression to tension, no, your direction doesn't matter. Sound good? But long story short, remember that formula I showed you, that sigma equals my over I? That's your m, basically. That's your m. So, and tau equals VQ over IB, that's your V. Sound good? Okay, all right. Here's what I'm thinking on this one. Okay, so here's the thing with this one. What time is it? It's 9:01. I'm going to be honest with you. I don't think we have enough time to properly explain this one right now in class. But considering that I might have some interesting scheduling conflicts over the next couple days, here's what I'm going to do, okay? I'm going to probably post a little video on this example. And I'll keep it short. I'm not going to make it like hours. I'll probably keep it short, like 10, 15 minutes max. But I'm going to post a video on specifically how to do this example. There's nothing hard, really majorly complicated with it. The only thing I want to say about this example is that when you look at the shear diagram, remember how I said that the amount of positive area has to equal the amount of negative area? Well, it's going to sound like I contradicted myself because that's not going to happen here. But that is going to be offset by a particular reaction. And I don't want to get too much into it without getting into the math, but suffice it to say that we will discuss this over the video, okay? Here's what I don't want to do. If I miss class on Tuesday or miss class on Thursday and we have to come back like a week and a half later, I don't want this example to be trailing off. I'd rather just post a video showing you how to do it, and then whenever we see each other again, we'll start talking about bending. All right? Sound good? Okay. So here's, just so you're aware, I think that in terms of your homework assignment, you are equipped to do probably most of it. This I don't think should be a major hindrance, but I will post a video on specifically how to do this example soon. Once I do that, you all are ready to get rocking and rolling on your homework, okay? Whenever we see each other again, we're going to talk about stresses and beams, okay? And so what we've talked about, geometric properties, shear and moment diagrams, and that's your second exam, okay? Because it's all going to sort of be focused on one topic. It's all going to be focused on beams, okay? Because it is a well-contained topic in and of itself. Sound good? So with that, I'm going to go ahead and call it a little early. You guys have a wonderful weekend. I will see you whenever I see you. Just pay attention to your email. That's all I was going to say. On this? Okay, all right.